What is the final temperature when 0.032 kilograms of milk at 11 degrees Celsius is added to 0.16 kilograms of coffee at 91 degrees Celsius? We're going to assume that the specific heat capacities of the two liquids are the same as water, and we'll disregard any energy transfer to the liquid surrounding. So the coffee isn't going to radiate any heat to the atmosphere. Now, we have the mass of milk. I'll just put MK. It's 0.032 kilograms. And the temperature, the initial temperature for milk, is equal to 11 degrees Celsius. Okay, it's added to 0.16 kilograms of coffee, so the mass of coffee is 0.16 kilograms. The initial temperature of the coffee is equal to 91 degrees Celsius. We're going to make the assumption that the specific heat capacities are that of water, so the specific heat capacity is equal to 4186 joules per kilogram Celsius and 4186 joules per kilogram Celsius. Now, the milk is starting off at 11 degrees Celsius, the coffee is 91. So the coffee is going to lose heat energy, the milk is going to gain heat energy. So the heat that is gained by the milk is equal to the heat lost by the coffee. So we start off with MC plus or minus delta T is equal to MC plus or minus delta T. Okay? The mass of the milk is 0.032. Specific heat is 4186. And now we have to think. The change in temperature. This is where the plus or minus comes into play. Delta T. The milk is warming up from 11 degrees to some equilibrium temperature. So that equilibrium temperature minus 11 is going to be the change. So this is going to be T minus 11. So we put T minus 11 here. Now that's equal to the mass of the coffee of 0.16 kilograms times specific heat capacity. That's 4186. And now we have to think. The plus or minus, the delta T, change in temperature. It's going to start out at 91 degrees Celsius. It's going to go down. So 91 degrees Celsius minus the equilibrium temperature, 91 minus T, is the temperature change, the delta T. So we have 91 minus T here. Now, these two are the most significant parts of the equation that you need to think through in order to get this right. If you just do temperature final minus temperature initial, you'll have to throw in a negative sign to one of the sides if you do TF minus TI. If you do it this way, the negative sign is taken care of by flipping. Notice this is T minus 11 and this is 91 minus T. So you've already put a negative sign in for the temperature decrease. Basically, it's a directional temperature change. Now, let's multiply this out. You have 0.032 times 4186, and you get 133.952 times T minus 11. That's equal to 0.16 times 4186, 669.76 times 91 minus T. Now we're going to distribute this through 133.952 T minus 133.952 times 11 is 1473.472. That's going to be equal to 669.76 times 91. That's 60,948.16 minus that. All right, now we have a T on this side, T on this side. Move this over, and then move this over. So 133.952 T plus 669.76 T is equal to 60,948.16 plus 1473.472. Alright, factor out the T. 133.952 plus that is equal to, I'm going to go ahead and add these numbers together. 60,948.16 plus 1473.472. This gets 62,421.632. Alright, and temperature is going to be 62,421.632 divided by the sum of those numbers, 133.952 plus 669.76. This is 803.712. And I divide these out. 62,421.632 divided by 803.712 gives us a temperature of 77.7 degrees Celsius. So our equilibrium temperature is about 78 degrees Celsius. The coffee is going to start out at 91 degrees. It's going to be cooled off to 78 degrees. The milk is going to start out at 11 degrees. It's going to be warmed up to 78 degrees.